I dropped my toast this morning, watched it tumble in slow motion, and knew with absolute certainty it would land butterside down on my carpet. And it did, just like it always does. Just like it does to you, to everyone, every single time. And for years, I thought this was Murphy's Law, the universe conspiring against me, bad luck written into the fabric of reality. But then I discovered something that changed everything. This isn't luck. This isn't randomness. This is pure deterministic physics. Emmy Noether's conservation laws playing out in my kitchen, and the culprit isn't fate. It's my table, specifically the 76-centimeter height that nearly every dining table in the Western world shares. And today I'm going to prove to you mathematically why your furniture is destroying your breakfast. Before we dive into the physics, I need to know, are you watching this on your phone during breakfast, on your laptop at work, or on your TV while eating dinner? And more importantly, have you experienced the butter side down phenomenon? Does it happen to you as consistently as it happens to me? Drop a comment below and tell me your most traumatic toast drop story, because I genuinely want to know if this is as universal as the research suggests. Let me start with Robert Matthews, a physicist who in 1995 published a paper in the European Journal of Physics, proving that the buttered toast phenomenon is real, not psychological bias, not selective memory, but actual physics. He won an Ig Nobel Prize for this work, those prizes that celebrate research that makes you laugh, then makes you think. And his conclusion was devastating. The phenomenon is real, and it's a consequence of the fundamental constants of the universe combined with typical household furniture dimensions. Your breakfast is governed by the same laws that govern galaxies, so let's break down what actually happens when toast falls. When I bump my plate and toast starts sliding toward the edge, something critical happens. One side of the toast leaves the table before the other side. This creates asymmetry. And asymmetry in physics creates rotation. Think of a seesaw. When one end loses support, the other becomes a pivot point. Gravity pulls down on the unsupported end, creating torque, rotational force. So my toast isn't just falling, it's rotating as it falls. And here's where Emmy Noether enters the story. Her theorem tells us that every symmetry in physics corresponds to a conservation law. Rotational symmetry gives us conservation of angular momentum. Once my toast leaves the table and becomes a free-falling object, its angular momentum is conserved. The rotational energy it gained from tipping over the edge continues throughout the fall. No external torque stops it. Air resistance is negligible, so the rotation rate stays constant all the way down to my carpet. This is why the outcome is deterministic, not random. The initial conditions completely determine the final orientation, and those initial conditions are nearly identical every time, because humans build standardized furniture and bakeries make standardized toast. I'm not unlucky, I'm just experiencing the inevitable consequence of angular momentum conservation in a 76-centimeter reference frame. Let me show you the math, because this is where it gets beautiful. Standard dining table height is 76 centimeters. This is nearly universal across Western furniture design because it's ergonomically comfortable for humans of average height. Evolution optimized our body proportions. Furniture designers optimized table height to match. Nobody thought about toast physics. Now my toast is roughly 10 centimeters by 10 centimeters. When it tips off the edge, it needs to rotate 180 degrees to go from butter up to butter down. Does it have enough time? Let's calculate. Using basic kinematics, the fall time equals the square root of 2 times height divided by gravity. Plugging in 76 centimeters, I get approximately 0.39 seconds. So my toast has 0.39 seconds to rotate. Now for the rotation calculation. The angular acceleration equals torque divided by moment of inertia. Doing the math, I get about 15 radians per second squared. Starting from rest, the toast rotates through approximately 1.14 radians or 65 degrees during free fall. But wait, that's not 180 degrees. So why does it land butter down? Because the toast doesn't start perfectly flat. It's already tilted about 20 to 30 degrees. By the time it's fully airborne, add the 65 degrees from free fall, and I get 85 to 95 degrees total rotation. Not quite a full flip, but enough that when the toast hits the ground, the butter side is facing down or at a steep angle that makes it flop butter down on impact. The math predicts that 76 centimeters creates exactly the wrong amount of fall time, too much, and the toast completes a full rotation landing butter up. Too little, and it doesn't rotate enough, also landing butter up. But 76 centimeters is the Goldilocks zone for disaster. The BBC actually tested this experimentally. They recruited 300 school children, gave them 100 slices each, 10,000 total drops from tables of various heights. The results confirmed the theory. At 76 centimeters, the toast landed butter down 81% of the time, not 50-50, 81%. But when they raised the table to 3 meters, the toast completed a full rotation and landed butter up 80% of the time. When they lowered it to 40 centimeters, it didn't rotate enough and also landed butter up. There's a death zone centered around 76 centimeters, where physics guarantees disaster, and humanity designed every dining table to sit right in the middle of it. Now here's what fascinates me about cultural variations. In Japan, traditional dining uses chabudai tables about 30 to 40 centimeters high. You sit on the floor. At this height, drop toast doesn't have time to complete the fatal rotation. Japanese households accidentally optimized against the problem. In some Middle Eastern and South Asian cultures, people eat on floor mats. Again, reduced height means reduced rotation. But Western Europe and North America, with our 76 centimeter tables, maximum toast destruction, American kitchen counters at 90 centimeters are even worse. Enough height for 1.2 rotations, which still lands butter down, but with more momentum, so it splatters harder. Your culture's furniture choices literally determine whether physics ruins your breakfast. So what can I do about this? What can you do? Here are my practical solutions. First, the table height hack. If you're designing a kitchen, consider bar height tables at 120 centimeters. This gives toast enough fall time to rotate past the danger zone or go Japanese with a 40 centimeter low table. Not enough time for fatal rotation. Second, the toast size trick. If you cut bread into 7 centimeter pieces instead of 10, you change the moment of inertia. Smaller toast might complete a full rotation, or go larger with 15 centimeter artisan slices that rotate more slowly. Either extreme escapes the death zone. Third, the push. Don't drop method. If I knock toast off the table, I try to give it lateral momentum, push it sideways. This changes the rotation axis, and the butter down probability drops closer to 50-50. Fourth, the quick catch reflex. 0.39 seconds is enough time for good reflexes to catch the toast mid-fall. Athletes and gamers can actually beat the physics. Or fifth, the nuclear option. Don't butter your toast. Butter side down is only a problem if there's butter. I know this defeats the purpose, but from pure physics, it's most effective. Noether would approve of radical simplification. But let me zoom out, because this toast situation reveals something profound about reality. We live in a universe that feels random. Things happen. We attribute them to luck or Murphy's Law. But underneath, there's determinism, rigid mathematical laws governing every motion. My toast falls butter down, not because the universe hates me, but because initial conditions feed into deterministic equations producing deterministic results. This is classical Newtonian mechanics in pure form, and it's deeply connected to Noether's work because her conservation laws are statements about determinism. Energy is conserved, momentum is conserved, angular momentum is conserved. These aren't probabilistic. They're absolutes. Given the initial state, the final state is completely determined. Yes, quantum mechanics tells us subatomic particles have genuine randomness, but at macroscopic scales like falling toast, classical mechanics dominates. My kitchen is operating in the deterministic regime. where Newton's laws reign supreme, and those laws say butter down at 76 centimeters every single time. So why does my toast land butter side down? Because my table is 76 centimeters high. Because gravity creates torque. Because angular momentum is conserved. Because Noether's theorem guarantees rotational motion continues until something stops it. Because evolution optimized my body dimensions. Because furniture designers optimized for ergonomics, not physics. Because 0.39 seconds is exactly enough for 85 degrees of rotation. Because 85 degrees is exactly enough to doom my carpet. It's not Murphy's Law, it's Newton's laws, plus Noether's conservation principles, plus human design choices, a perfect storm of physics and culture and accident. Next time you drop toast, don't curse your luck. Appreciate the mathematics playing out in real time. You're watching rotational dynamics, gravitational torque, moment of inertia, angular momentum conservation, all of classical mechanics condensed into one falling slice of bread. Your kitchen is a physics laboratory. Your breakfast is an experiment, and the results are written by equations discovered hundreds of years ago that will remain true billions of years into the future. Now here's the final twist. Now that you know this, physics, you can't unknow it. Every time you see toast on a table, you'll think about the death zone. You'll calculate rotation in your head. You'll predict the outcome before it happens. I've cursed you with knowledge, and it'll make you paranoid about plate placement for the rest of your life. But seriously, this is what I love about physics, the ability to take something that feels random and frustrating and reveal the hidden order underneath. The universe isn't random, it's just complicated. Emmy Noether spent her life uncovering these rules, and we're still finding applications. So, next time your toast lands butter down, remember you're experiencing conservation of angular momentum in a 76 centimeter reference frame. Blame your table, not your fate. Murphy was right, but Noether explained why. If you found this fascinating, please hit that subscribe button, because I'm breaking down more everyday physics mysteries through Emmy Noether's lens. And I want to hear from you. What everyday phenomenon should I tackle next? Why do earphones tangle in your pocket? Why does hot water freeze faster than cold? Why do traffic jams appear from nowhere? Drop your suggestions in the comments and I'll pick the most interesting one for the next video. Thanks for watching, and remember, physics is happening all around you, even in your breakfast.